Okay, so we're back here for the second part of the chemistry lectures. And again, I'm going to try to move through these quickly because hopefully most of it's a review. But like I said before, if for some reason this is too fast for you, please set up some time with me and I am more than happy to go over this with you. And like I said, a lot of this we are going over because, we're going to use some of these terms. You need to kind of understand what an ion is, and why these ions can create these kind of electrical charges across the membrane, being that they're charged particles. So again, these things are all going to become important. I know it's hard to picture now, but they will become important when we get into the physiology of things. So hang in there with me. Like I said, we're not getting into the nitty gritties. This isn't a chemistry class, so I'm not going to give you a bunch of like chemical reactions and have you like come up with the products or things like that. We're not doing that. I just want you to recognize, what is an ionic bond? What is a covalent bond? Which one is a transfer of electrons? Which one is sharing? Which one, of those bonds is going to form actual anions and cations? So again, those are that's kind of at the level that I'm going to be expecting for this. So, and I'm sure that you'll also get a better idea of what I'm looking for when you take the chemistry quizzes. So, and the level that's why I have those quizzes. The lecture quizzes are designed to really help you kind of guide you to what I expect for the exams. Okay. So I'm going to go ahead and turn off my video as I always do because it just seems to be a little bit delayed. And I'm going to go ahead and pick up right where I left off. So we left off talking about these exchange reactions. So we talked about synthesis reactions. We talked about which again are kind of these they're part of the anabolic building processes. We talked about decomposition reactions, which are breaking things down. So this is a catabolic reaction. And then lastly, we talked about these exchange reactions. Now the exchange reactions are where we're not only, breaking bonds, but we're actually building bonds as well, right? Because we're kind of exchanging things. So here we're breaking a bond between A and B, but then we're forming a new bond between A and C. So it's not a synthesis reaction, it's not a decomposition reaction, it's kind of both, right? And that's what an exchange reaction is. So when we talk about in living systems, one of the most important exchange reactions that we will talk about are these reduction oxidation reactions, or what we call your redox reactions. So I know some of you are like, no, not redox reactions again. But again, we're going to try to keep this kind of basic. It is important that you just understand the basis behind redox reactions, because we are going to talk about redox reactions again later on in the semester with physiology, especially when you get into 202 and blood chemistry and things like that. Redox reactions are very important. So the basis behind redox reactions are that there are atoms that are going to be reduced when they take on or gain electrons. And when they do that, when they take on and gain these electrons will form more high energy bonds. So it's kind of confusing because the term reduced has to do with the overall charge, right? If you're gaining electrons, you are gaining gaining negative charges, and that's the idea behind reduced, okay? So again, you're going to be gaining these electrons, but those electrons are going to be used in these high energy bonds. So what I want you to do is associate anything that's reduced is going to now have higher energy bonds, okay? So it's kind of in the term, this is, you guys are going to see why I don't write very much on this, but you can write high energy. This is my horrible attempt at writing here, okay? So again, it's weird because reduction actually usually means a gain in energy. So a reduction in overall charge, but gain in energy, okay? And then things that are oxidized are going to lose electrons. So that's where this mnemonic comes from. You guys probably have heard this if you took 181, the oil rig. So oil, OIL, is oxidation is loss, meaning you're losing electrons, and reduction is gain. Okay, so you're gaining electrons. So when you gain those electrons, you're gaining energy. When you're losing those electrons, you're losing some of the energy. So in this example, think about, glucose and the breakdown reaction that we have in our bodies, the breakdown of glucose to transfer the energy in these high energy glucose bonds to a form that's usable for us, right? In the form of ATP. So in this redox reaction, okay, in this example here, glucose is going to be oxidized, right? It's going to lose electrons as we break it down. And as we break down those high energy bonds in glucose, we're also going to lose the energy from those bonds. Now, we don't necessarily lose the energy, right? Because this is an exchange reaction. So we're just exchanging it. And as we exchange those electrons and the energy in those high energy bonds, we're going to put them into a usable form called ATP, okay, into these high energy phosphate bonds now, right? And so here, as our, this molecule here is going to be reduced because we're actually gaining some electrons and we're going to gain that higher energy. So this is a redox reaction. In this case, again, when you look at glucose is oxidized, okay, then here, the oxygen molecule is going to be reduced because this oxygen molecule is going to take on some of these high energy electrons, right? And eventually, through that whole electron transport system, it's going to transfer them to the ATP, okay, into the form of ATP. So that's kind of the basis behind these redox reactions. So again, it's just an exchange reaction. It's really an exchange of energy in the form of electrons, okay? And again, oxidation is loss, again, meaning that you're losing the electrons and also kind of losing some of the energy in that from that high energy bond, or I should say exchanging it, and then reduction is gain. So gaining electrons and then gaining some of that higher energy, those high energy electrons to form these high energy bonds, okay? So that's what's happening here when we break down glucose and transfer that energy, exchange that energy into a usable form that our cells can use, ATP, okay? So again, I'm gonna say very basic. That's as detailed as we're gonna get. I am not going to get super detailed onto redox reactions. That's for your chemistry class. This is as much as we'll get into, okay? And that, again, the idea is just that you kind of understand the basis for redox reactions so that when we do talk about them in things like blood chemistry, you'll kind of know the basis for that reaction. Okay, now energy flow in chemical reactions. All chemical reactions are what we either call exergonic or endergonic. And this is super easy. Exergonic reactions are going to result in a net exit or release of energy. So there's my little trick for you. You can think exergonic energy's exiting or releasing energy. So it's giving off energy, okay? And so the products end up having less potential energy than the reactants did. So these are obviously going to be like your catabolic reactions, your breakdown reactions, and your oxidative reactions, right? So again, things that are being oxidized are moving down on that potential energy, right? So keep that in mind. Just like here when we talk about glucose is oxidized, you know, as we break the bonds down, it moves down, right? In energy, it's got that loss of energy, the loss of electrons, okay? So those are exergonic reactions. Now, endergonic reactions result in a net absorption of energy. So they use up energy. So these are going to be in things like your anabolic or building reactions. And you can keep in mind that the terms, if you are having trouble remembering anabolic, which one, a catabolic, which one are building and which one are breakdown reactions, just kind of remember that there's anabolic steroids. So I think I even have a picture somewhere. I thought I had a picture somewhere of of like Arnold Schwarzenegger, and he's got these, big muscles. So you can think of, not that he did anabolic steroids, but steroids, anabolic steroids are building reaction. They build, right, muscles, just to kind of help you relate that term. And so those are anabolic reactions. Anabolic reactions don't get me wrong, they don't have anything to do with steroids, but I'm just kind of trying to help you relate that term. But anabolic reactions are just any building reaction. Anything. Maybe we're taking amino acids and building a protein. Maybe we're taking simple carbohydrates and building a more complex carbohydrate. Okay, those are all anabolic reactions. Maybe we're taking lipids and putting them together to form triglycerides. That's an anabolic reaction. Okay. And then catabolic reactions would be just the opposite. Anytime that we're breaking those down. So let's say we're breaking down lipids, okay, and releasing energy, hence exergonic, right? Or maybe we're breaking down these complex carbohydrates into simple carbohydrates and releasing energy from those bonds. That's exergonic, okay? So hopefully that kind of helps you relate these chemical reactions, and this is a good slide to kind of like put it all together. Reversibility of chemical reactions. All chemical reactions technically are reversible, and again, we're going to get into this as we talk about enzymes. Usually, if you have a chemical reaction here, A plus B forms AB, okay? The reason, let me put my pen on here, but the reason that A plus B forms AB, okay, and goes this direction is usually you have enzyme 1 here, okay? You have a lot of enzyme 1 here, and it's going to help this reaction. I'll talk about enzymes in just a minute if you don't remember what they do, but it's going to help this reaction go this direction, okay? Now, all of a sudden, enzyme 1 might all of a sudden decrease, okay, in concentration, and enzyme 2 now increases in concentration. Enzyme 2 will actually reverse this reaction, help the reaction go this way. So, and then now AB can be broken down. Okay, so most of our reactions are reversible and they can go either direction. It just depends on whether or not you have enzyme 1 making it go this way or enzyme 2 making it go this way. Okay. A chemical equilibrium can occur if neither a forward nor reverse reaction is dominant. So the reaction's going both ways. That's when we get chemical equilibrium. Okay. And many of our biological reactions are not very reversible, meaning that there is an energy requirement to go backwards, and that energy requirement is too high, and we don't have maybe the enzyme to do it. So that ends up being what drives our reactions in one direction versus the other. Okay. So, and we'll talk about this more. Enzymes are really going to be the key here to which direction a chemical reaction goes. So we'll talk about this in just a minute here. But I just want you to know that many that chemical reactions are reversible, even though they might not be that reversible in the human body, depending on what enzymes we have. Now, the rate of chemical reactions, as you probably know, are affected by different things. And this is important to understand because this is one of the main reasons, guys, why we maintain homeostasis, okay? Is because the temperature, the concentration of reactants, the particle size, pH, all those things are going to affect the rates of our chemical reactions. So, as you can probably guess, some of the main things that will affect the speed of chemical reactions are 1, temperature. As you add, again, heat energy to something, it's going to speed up the molecules, and that's going to increase the rates of reaction, okay? So, again, anytime, even when your body is warmer, okay, the rates of chemical reactions are going to occur at a faster rate. If you're really cold, those rates of the reactions will kind of slow down, and oftentimes that's what makes you feel really sluggish if you're really cold, okay? Now, I say really cold because remember that your body is going to do things to help maintain homeostasis, right? So your body is going to try to maintain a constant body temperature that's going to keep your rates of chemical reactions at the perfect rate, okay? So keep that in mind. So again, that would be like if you're like hypothermic, and your body temperature is really, lowered below what it should be because you couldn't maintain homeostasis. That's when rates of chemical reactions are going to slow down. Okay. But again, the main reason why we maintain an ideal body temperature is because that's the ideal rate at which we need our chemical reactions to happen. So kind of interesting. That's why we keep these, body temperatures around 98, 98.6, everybody's a little different, but degrees Fahrenheit. That's why. It has to do with the ideal rates of reactions. Now, concentration of reactants, of course, is going to make a difference. The more reactants you have, the faster the rate of that reaction is going to be, right? The fewer reactants that you have, then the slower that rate of reaction is going to be. So that's pretty easy, right? Particle size. So smaller particles actually usually increase the rate of reaction, believe it or not. So as those smaller particles, actually, as they're moving around, they actually usually end up causing the rates of reaction to be higher. And so we'll kind of get into that as we go throughout. One of the main reasons, and then these are just a few things that affect the rates of chemical reactions, but guys, there's lots of other things. So pH can also affect the rates of our chemical reactions. So we're going to get into this when we talk about enzymes. The name of the game is, what is the ideal environment for our enzymes? So the main thing that's going to affect the rate of our chemical reactions are these biological catalysts that we call enzymes. Now, just as a reminder, a catalyst is anything that can increase the rate of reaction without actually being chemically changed or becoming like a part of the chemical reaction. So the enzyme is just this kind of outsider that's helping the chemical reaction along, okay? And so again, we're going to primarily use the term enzyme. An enzyme is a type of catalyst, but it's our biological catalyst. So we're primarily going to talk, when we talk about catalysts, we're primarily going to talk about enzymes as increasing our rates of reaction. So what enzymes do is they usually, again, provide these substrate binding sites. So that way then, again, that chemical reaction can happen a bit faster. So a lot of times, if it's a breakdown reaction, it might bind the substrate. And as it binds that substrate, it kind of puts it in the right conformation to where it makes it more easy for the bonds to break in a breakdown reaction, okay? So an enzyme is going to kind of lower the energy that's needed for this reaction to happen, okay? Whether it be a breakdown reaction or a building reaction. Enzymes, there will be different enzymes for different reactions and the reactions going different ways, okay? So enzymes, again, their main function is to increase the rate of reactions that go on in your body. And they, again, are so important that our body could not function without enzymes. The rates of the chemical reactions, they would still happen, but they would happen so slowly we couldn't function, okay? And so the enzymes actually speed up those rates of reactions so that they happen at an appropriate rate for us so that we can function, right? Because we have these high metabolic, high energy needs. And so we need those rates of reactions to occur quickly. So when you talk about homeostasis inside the human body, the majority of the homeostatic mechanisms are meant to keep our enzymes happy and functioning at their best, okay? So again, pH, we like to maintain a certain blood pH because we like our body to have a certain pH where our enzymes are functioning at their best. Now, what's cool is that we have different enzymes that will function better at different pHs. So for example, you're going to have enzymes inside the stomach that require a really acidic environment to be activated. So again, so we can even create little pockets inside the body, right? That have the perfect contained environment for your enzymes, okay? So inside your stomach, you have enzymes that are needed to break down proteins. And we'll talk about this when we get into 202. But those enzymes require an acidic environment to be active. So, I mean, again, this is one of those things where you're like, the body is just amazing. Like, how does it work this well? And to be honest, when you get through this course, when you get through anatomy, you're going to be like, I am amazed. I am like astounded that not more goes wrong inside the human body with all that has to happen. So I hope that you find it as fascinating as I do by the end of this course. And then this is just a funny meme for you. I won't read it because you could read it, but you know, now you have enough chemistry to actually understand these very nerdy memes. So I'll put in a few for you. Sorry about that, just so you can see how nerdy we've all become here. So what I'm going to do, I'm going to pause this and open up the next part 2 lecture for you. So we're going to move right along into the second part of this chemistry lecture, which I think you'll enjoy a little bit more because it's the biochemistry side. I don't know about you, but personally, biochemistry was my favorite. But again, that was because at heart, I just love studying living organisms. So chemistry applied to living matter is a lot more interesting to me. So that's what biochemistry is. It's just, again, the studying the chemical composition and reactions in living matter. And that's primarily what we're focused on, right? In human anatomy and physiology, because we're obviously a living organism. So again, all chemicals are either organic or inorganic. So when we talk about things that are organic, these are going to be things that contain carbon, are usually large, and they're covalently bonded, okay? So we have a lot of carbon hydrogen. So our organic compounds are going to have carbon hydrogen bonds, carbon bonded usually to hydrogen, okay? And they're usually large. These are going to be things like carbohydrates, fats, proteins, and nucleic acids. Those are going to be the major organic compounds that we're going to talk about and the ones that you are going to be responsible for knowing. Carbohydrates, fats, proteins, nucleic acids. Okay. Now our inorganic compounds are going to be things, again, that are ionic or covalent. It can't be covalently bonded too. But if it's covalently bonded, there are no carbon hydrogen groups, okay? So again, it's inorganic if it has no carbon hydrogen groups. And if it's, again, ionic, or again, sometimes it can be covalent. So you can't just say organic is covalent and inorganic is ionic salts, right? Because there are some, you talk about water, right? Water has covalent bonds within the water molecule, but there are no carbon hydrogen groups. So we know it's inorganic, okay? So inorganic compounds that you need to know: water, salts, and many of our acids and bases, okay? So again, things like hydrochloric acid that we're going to have inside the stomach, which is HCl, okay, is an acid. Or we'll talk about things like bicarbonate, which are bases, okay? And it says they do not contain carbon, but that's not necessarily true, because there are some inorganic compounds that do contain carbon, but they don't contain these carbon hydrogen groups. Okay, so that's the big thing. They don't contain the carbon hydrogen groups. All right. So they're both equally essential for life. We obviously require water. We're mostly water. We require salts. We require acids and bases to survive. And then we require all these organic compounds: carbohydrates, fats, proteins, and nucleic acids. Okay. So let's talk about these inorganic compounds first, and then we will finish up with the organic compounds. Obviously, our most important, I shouldn't say most important, most abundant inorganic compound inside the human body is going to be water. And it's going to account for anywhere from 60 to 80% of the volume of living cells, okay? So we're really kind of these like big bags of water. And when we talk about the solutions inside our body, right, the solvent is primarily going to be water for most of the solutions inside our body. So obviously water is a really important inorganic compound in the human body. Now, because it's this really important inorganic compound, we need to understand some of the properties of water, okay? So one of them is that water has this high heat capacity, okay? And what that simply means is that it takes a lot of energy to change the temperature of water. This is why, again, I have this picture here, this image of, a fish, and the fish is like, I love the specific heat capacity of water. And that's because, again, as the ambient temperature around us changes outside drastically, okay, it takes a lot more energy to change the temperature of water. So water actually maintains a more consistent temperature, okay, and that's because it just has this high heat capacity. It takes a lot of heat to change its temperature, okay. We'll also talk about the high heat of vaporization. Again, it takes a lot of energy to cause those molecules, again, to be released as a gas. We'll talk about its polar solvent properties because it is a polar molecule. It's reactive and how it acts to cushion, okay. Oh, I guess maybe I'll talk about it all here. Really quickly, again, this is where you just have to know this very basic level. I'm sorry, I thought I teach a marine biology course and I go over, obviously water pretty in depth. So, I was thinking I had another slide, but, really quickly, again, high heat capacity just means it takes a lot of energy to change the water temperature. And again, you know this because again, you've gotten in a pool in the summertime, right? And thankfully, the water temperature in the middle of the summer doesn't change as much. It'll be like 120 degrees outside, and thank goodness, your pool is maybe 89 degrees, okay? So we also love the high heat capacity of water out here in Arizona. High heat of vaporization, again, it takes a lot of energy to cause those molecules to speed up fast enough that they're going to become a gas, okay? Polar solvent properties are just that water molecules are polar, and remember that, so they're slightly charged. They have a slight positive and a slight negative charge, right? And that makes it so that water molecules want to interact with other water molecules, right? Or they want to interact with other things that are charged. That's why water likes to dissolve salt, right? Because remember that oxygen on the water molecule has a slight negative charge and the hydrogens have a slight positive charge. So this makes water reactive. It likes to interact with things because it's actually charged itself. And just as a reminder, just from the other lecture, okay, remember that water looks like this. You've got that oxygen bully up here. It's sharing electrons with these hydrogens here, okay? And remember that because oxygen is going to pull those electrons closer to it because it's more electronegative, it is going to want it's going to want those electrons to spend more time with it, and because of that, it's going to give this a partial negative charge on the oxygen end, and then these hydrogens are left with a partial positive charge. Again, it's just a partial charge because they're still sharing, just unequal sharing, okay? And so this will make water want to react with other things. This is what gives water its properties of cohesion and adhesion, meaning that water molecules like to interact with other water molecules because that oxygen, if it bumps into the hydrogen of another water molecule, then you'll get a hydrogen bond, right, between that partial negative charge of the oxygen and the partial positive charge of the hydrogen. So water molecules like to interact with other water molecules, but they also like to interact with other things, right, that are charged. And so this is why, when you use a little capillary tube, why water likes to stick to the capillary tube itself, okay? So again, water is charged and it makes it reactive. Water also provides this great cushioning solvent, right? And so you're going to see that we have a lot of things like our serous fluid, remember, in those cavities around the heart, like the pericardial cavity around the heart. That serous fluid is mostly water, and it helps to cushion, again, provide some cushioning as the heart contracts, okay? So again, just a couple important properties of water that you want to make sure that you understand because, again, we're kind of these big bags of water. So salts are also very important. They're these ionic compounds, again, that dissociate into their ions. So again, just like, sodium, when we talk about sodium chloride, again, there's an ionic bond between the positively charged sodium, which is, if you remember, a cation. I know I'm bringing this back. And then chlorine, which is going to have a slight negative charge, right? Because it took the electron. Sodium gave up to it, right? So now it has that negative charge and it's an anion. And so what an ionic bond is, again, a bond just based on attraction between the positive charge of the cation and the negative charge of the anion, okay? And so that's what your salts are. That forms a salt, okay? And so when we mix these salts in water, then these ions now want that, now they'll bump into water molecules and they'll form, temporary bonds with the water molecules, okay? And so that will break apart these ionic bonds as you dissolve, a salt in water, okay? Now, all ions are what we call electrolytes because they can conduct electrical currents in solutions. So ions are going to play, obviously, a very specialized role in body functions. And so when we talk about, when you're talking about looking at the electrolytes in someone's blood, the reason that you care about these electrolytes is that, again, they're going to be very important for certain types of reactions, and they can even conduct electrical currents, especially when you're talking about things like sodium and potassium and calcium. And we're going to talk about how sodium, potassium, and then calcium are important for things like nerve conduction, creating these electrical currents for nerve conduction, as well as muscle contraction, okay? So those ions are going to play very specialized roles. They're very important, and that's why we care about these ions that make up the electrolytes in our body. Now, the ionic balance, again, is going to be really important for homeostasis, meaning if you can't keep your blood calcium levels, to a homeostatic normal level, let's say your blood calcium levels get too low, it's bad because you can't do muscle contraction without calcium in your blood. So like all of a sudden your muscles lose the ability to contract, right? That's really bad. Same with sodium and potassium. If you don't have enough sodium and potassium in your body, then you lose the ability to do things like nerve conduction. This is bad, right? It's very bad. So this is why our ionic balance is so important. And that's why many of the mechanisms that we have in our body, especially as you're going to get into talking about things like, when you talk about the blood lecture, you talk about things that are happening in the urinary system, you're going to talk about maintaining these ionic balances, okay? And then common salts in the body, again, are going to be things like sodium chloride, calcium carbonate, potassium chloride. Again, you can see it has these very key electrolytes. Sodium, especially chloride, is going to be another one. Calcium is very important. Carbonate is going to be important because we're going to talk about the bicarbonate system in the blood. Potassium is going to be very important. So again, we're not going to get into it now. You don't have to know all these now, but you need to know that these common salts in the body have very important roles as, again, they break up into their ions that we call electrolytes. Okay. Now, acids and bases are both electrolytes because they will ionize and dissociate in water. So remember what an acid is an acid is any proton donor, meaning that they're going to release a hydrogen ion that has a positive charge. That's what we call it, a proton donor, okay? So again, these are bare protons. It has no electrons in its solution because if you have a hydrogen ion, right, that means that it lost its only electron, okay? Because hydrogen ions have one proton, one electron. So for it to be H+, it means it lost its only electron, okay? So that's what we call these proton donors. So for example, if you take hydrochloric acid, right, in water, it can dissociate into hydrogen ions and chloride ions. And it's these hydrogen ions that make things more acidic, okay? So important acids, especially in the stomach, we have hydrochloric acid in the stomach. Acetic acid is actually our vinegar. And then bicarbonic acid is going to be really important for our blood chemistry, okay? Bases are going to be just the opposite. So if acids are proton donors, bases are proton acceptors. They're going to be anything that picks up those hydrogen ions that are in solution. So for example, when you talk about sodium hydroxide, okay? So sodium hydroxide will break up into sodium and hydroxide ions. And when, again, that happens when we dissolve this base, sodium hydroxide, in a solution like water. It's going to release this hydroxyl, what we call a hydroxyl ion. That's what we call it, sodium hydroxide. And that hydroxyl ion can then go bind up a hydrogen ion. So think about it. If this hydroxyl ion comes into contact with a hydrogen ion, what's it going to make? You got it, right? It's then going to form a bond here and make H2O, which is water, which is neutral, okay? So now you have, again, that's what a base is doing, right? It can neutralize some of those hydrogen ions, okay, that are in solution. So important bases are going to be things like bicarbonate. Again, we're going to talk about this in the bicarbonate system in the blood, okay? And then ammonia is also another important base, okay? So you can see here, this is an acid releasing hydrogen ions into solution, a base, which is going to release hydroxyl ions that can then go bind up those hydrogen ions, right? And then you have salts, which are neither acidic or basic. They're just releasing ions, right? But not hydrogen ions, not hydroxyl ions, okay? Makes sense? And so I just put this as your bicarbonate buffer system because you're going to see it's pretty cool. This whole system in your blood is designed to have a weak acid and then break down into a base and then the hydrogen ion. And when we get to blood chemistry, we'll talk about this being this kind of awesome buffer system in your blood, okay? So again, this is why we just keep it in mind that acids are anything that can release hydrogen ions in solution, and bases are anything that can bind up hydrogen ions, okay, in solution. And that's what's happening here when bicarbonate ions run into a hydrogen ion. So that's why this is a base and this is an acid, okay? And what we call this type of system where it can go either way, a buffer system. So again, just kind of something to keep in mind because you'll get into that into 202. So remember, our acid-base scale is what we call our pH scale. And our pH scale is simply just a measurement of the concentration of hydrogen ions in solution. The more hydrogen ions in a solution, the more acidic that solution is. Now, because pH is a negative logarithmic function of measuring our hydrogen ions in moles per liter, it's going to go from 0 to 14. And you don't necessarily have to understand this now, but if you look here, it's confusing because when you talk about things that are pH 14, it's talking about things that have 10 times the negative 14th hydrogen ions, which means they have fewer actually hydrogen ions. If this is too much, you don't understand, like this makes sense to me. And so this helps me to, as I was a student, remember why a high pH is more basic and why a low pH is more acidic, because the lower pH actually has more hydrogen ions. You're only like here, pH 1 is 10 to the negative 1, okay? Versus, 10 to the negative 14 is way, way fewer hydrogen ions, okay? But if that doesn't work for you, and you're like, whoa, you just confused me, I don't even want to think about what you just said, then all you have to do is just remember 7 is neutral, below 7 acidic, above 7 is basic, okay? So, yeah, that's one thing that you have to remember, okay? So the lower the pH, more acidic, the higher it is, the more basic. 7 is neutral. And then the other thing that you have to remember is that the pH scale is logarithmic, meaning that every difference in pH is tenfold. This I do want you to know, because when we talk about blood pH and maintaining a constant blood pH, it's very important to realize that if your blood pH changes by just 1 pH point on the pH scale, that is a change of times 10 because it's logarithmic. It's a tenfold change. So a pH 5 solution is actually 10 times more acidic than a pH 6 solution, okay? So there's not just a 1-fold change, it's a 10-fold change with each pH point, okay? So again, acid solutions are going to be anywhere between 0 and 6.99. Okay, so we have a higher hydrogen ion concentration. And then neutral solutions are going to have an equal number of hydrogen and hydroxyl ions. That's going to be pH 7. And that's pure water, okay? Pure water is neutral, pH 7. And then alkaline solutions are going to be anything that's above pH 7, okay? pH 7 to 14 is going to be our alkaline or basic solutions, okay? So again, keep in mind that there is a 10-fold change here. So if you were talking about here, you are at a blood pH of about 7.4. If you go into the hospital and they check your blood and your blood pH is 6.4, you don't want to be like, oh, that's just change of 1 on pH scales. No big deal. No, that's a huge deal. That's very bad, because that means that your blood, if it's at pH 6.4, it is 10 times more acidic. 10 times. This is bad, okay? So that is why it is very important to understand that pH is a logarithmic scale, okay? Now, neutralization reactions are just simply when acids and bases are mixed together, okay? And they neutralize each other. So here, this is just a very simple displacement reaction. You have sodium hydroxide and hydrochloric acid. What happens is, again, we just have a simple displacement reaction. The sodium, again, when mixed in solution, the sodium can bind to the chloride and form an ionic bond. And then the hydroxyl would be released here. The hydrogen ion would be released here. These two can come together to form water, okay? So now we just have salt and water, which is neutral, okay? So that's where you had your acid and base neutralize each other. That's what we mean when we say a neutralization reaction. So we're going to have buffer systems to do this, to help us maintain a normal pH inside the body. And so buffer systems are basically to help either bind up extra hydrogen ions in solution. If those, again, hydrogen ions you have a bunch of those hydrogen ions in solution. So things like our bicarbonate can go bind to those hydrogen ions and form, again, this weak acid. That's our carbonic acid. Or, again, if we don't have that many hydrogen ions in solution, then that carbonic acid can break down into bicarbonate and our hydrogen ions, okay? So all this does is our buffers convert strong acids or bases completely dissociated into weak ones, okay? So this is our carbonic acid bicarbonate system. And so what happens here is if you've got carbonic acid and all of a sudden the pH rises, okay? So again, it becomes more basic, then this carbonic acid can break down and release some of these hydrogen ions into solution, okay? Now, if for some reason there's a drop in pH and we all of a sudden have lots of hydrogen ions in solution, those hydrogen ions are more likely then to bump into that bicarbonate and form carbonic acid. Okay, and this helps to keep our blood pH, okay, more neutral. So we have this nice buffer system. Again, I'm not going to get too into this. I just want you to basically know that buffers resist these changes in pH, and they help us to maintain homeostasis. So I just want you to know they can release hydrogen ions if the pH rises, and they can bind hydrogen ions if the pH falls. Okay, this is basically what I want you to know right here about buffers, right here. But I'm introducing this because this is the buffer system that we're going to talk about in the blood. So while I'm talking about buffers, I might as well introduce a little 202 there, okay? Now, let's get into organic compounds. So now we've talked about our inorganic compounds, why they're important. This last section of this lecture is going to talk about organic compounds, okay? So organic molecules are going to be those that contain carbon, especially carbon-hydrogen bonds, okay? So our exceptions for organic molecules that contain carbon are going to be things like carbon dioxide. Carbon dioxide is not organic. But if you think about that rule, it has to have a carbon-hydrogen bond. Carbon dioxide doesn't have a carbon-hydrogen bond. So again, it's going to be inorganic. Same with carbon monoxide. No carbon-hydrogen bond. Boom, it's inorganic, okay? So try to keep in mind that organic molecules need those carbon-hydrogen bonds. Carbon is going to be electroneutral. So it shares electrons, right? It never wants to gain or lose them. It just wants to share. So it always wants to form 4 covalent bonds with other elements, okay? And carbon is this very unique element to our living systems in that it forms these major organic compounds, okay? It's going to form our carbohydrates, lipids, proteins, and nucleic acids. Okay? So those are 4 major organic compounds that we're going to talk about. Now, all of these organic compounds are going to be synthesized and broken down through something called hydrolysis in the same type of reaction, which is kind of cool. So all 4 of these reactions, all 4 of these molecules are made in the same type of reaction, and they're broken down with the same type of reaction. Kind of cool, right? Makes it a little less that you have to remember. That's what I like, right? So when we make any of these organic compounds, we're making polymers, okay? We're going to take chains of these smaller building blocks called monomers, and we're going to put them together in a reaction, a building reaction called dehydration synthesis, okay? So what that means is whether or not we're making carbohydrates, okay, we do it via dehydration synthesis. If we're making lipids, we do it through dehydration synthesis. If we're making proteins, we do it through dehydration synthesis. If we're making nucleic acids, we do it through dehydration synthesis. All of them are made through dehydration synthesis. Cool, right? Phew. Less that you have to remember, right? Now, all of them, if you're breaking down a carbohydrate, or if you're breaking down a lipid, you're breaking down a protein, or you're breaking down a nucleic acid, all of them are broken down by the same reaction, which is a hydrolysis reaction, okay? So again, whew, easy to remember. Those are just the 2 reactions that you have to remember for all 4, okay, of those organic compounds, right? Okay, so the only difference is going to be that they're going to have different monomers, okay, that make them up. So again, this is just your basic dehydration synthesis. You're synthesizing a molecule. And the great part is, guys, the reaction name tells you exactly what is happening. Beautiful, right? Don't expect this all the time. Just enjoy this little lovely nugget, okay? So here in dehydration synthesis, you're going to synthesize, right, a polymer by dehydrating, removing a water. Beautiful, right? I love the simplicity of the name. I wish we did that all the time, but we don't, in science. We like to complicate things. So again, here we're going to put monomer, we're going to form a bond between monomer 1 and monomer 2. And so we're synthesizing a polymer by doing that. And in the process, we're dehydrating or removing a water molecule, okay? By taking a hydrogen from here and hydroxyl group from here, putting them together to form water, okay? And that allows us to make that bond between the polymer. Beautiful, right? Now, the breakdown reaction of any polymer into its individual monomers is hydrolysis. And again, the simplicity is beautiful here because the name says what it does. So check it out. Hydro means water. Lysis, right, means to break or cut. So you're literally breaking apart a water. You're lysing a water and using it, right, to break down this polymer. So what you do is you've got your polymer, right, linked by a covalent bond. Here comes in comes a water molecule. Again, you have enzymes to make these reactions happen. In comes a water molecule. That water molecule is lysed, broken up into its hydroxyl and hydrogen ion, okay? And a hydroxyl group goes on one monomer, hydrogen ion goes on the other monomer. As we break apart, we break that covalent bond in that polymer. Beautiful, right? I mean, the simplicity, you just gotta love it in the name, okay? Again, enjoy that moment where you've got, it actually makes sense, right? The name makes sense. Okay, so a very simple example of these reactions would be if you take glucose and fructose, 2 monosaccharides, okay, and you want to make a disaccharide, a polymer, okay, then you're going to do dehydration synthesis, right? We're going to remove a water, hydroxyl group from here, hydrogen ion here, going to come together, and that water molecule is going to be released as we form a bond between the glucose and fructose molecule. And guess what disaccharide this is? It's sucrose. So you just made sucrose through dehydration synthesis here. Okay, now when you want to do the reverse and you want to break down this bond in sucrose because you just ate some, sugar, and your enzymes are wanting to break down these more complex sugars into simple sugars. So again, we can, use the energy in those bonds. So as you break this down, you're going to do hydrolysis, literally hydrolysis, right? Hydrolysis. So you're going to obviously need water, and that water is going to be lysed, broken apart, and you're going to put a hydrogen ion on the fructose and a hydroxyl group on the glucose here, okay? So that's hydrolysis. So if you think about it, water is really important, especially for digestion, right? Because as you're breaking these bonds and doing hydrolysis, you need water, okay? So this is why you need water as you're eating food and breaking it down, okay? You need water to break down those bonds because of hydrolysis. All right, so those reactions are pretty easy. Make sure you know those reactions. Let's get into, lastly, a little bit of information on each of these organic compounds. We're going to start with carbohydrates. Obviously, carbohydrates are going to be things like sugars and starches. You guys all know that. It's pretty easy. You've probably known that for years. They're going to contain, obviously, carbon, hydrogen, oxygen. And the reason that they're called carbohydrates is you have this hydrogen and oxygen are in this 2-to-1 ratio. So literally the name actually means carbohydrate. Real quick, I'm just going to show you. Carbo, C is the carbo. So carbo means carbon and hydrate means water. So H2, oh my gosh, my writing is terrible. I really wish I had a better pen system. H2O for you, okay? So what that means is the ratio of carbon to hydrogen to oxygen in any carbohydrate will be 1 to 2 to 1. Okay, that's all that means. Pretty simple. So that's where it gets its name, carbohydrate, if that helps you. There are 3 classes. There's monosaccharides, which is your simplest monomer. That's your smallest unit of a carbohydrate. So you should know the monomers of each of these organic compounds. So you want to know that the monomer of carbohydrates is monosaccharides, okay? When you put 2 together, obviously now it's no longer mono, 1, but it's di, so disaccharide, okay? 2 sugars. And then if you put any more than that together, okay, 3 or more, then it becomes a polysaccharide, okay, many sugars. So again, and that's where you're going to make those more complex carbohydrates or polysaccharides. There's your my lovely cheesy meme for you. Okay, now you guys are getting all of these nerdy memes, right? I'm so sorry, it ruined you forever. Okay, so again, here's the general formula. It's like just what I showed you. These are these simple sugars containing 3 to 7 carbon atoms. Our monomers, again, are carbohydrates, and we put those monomers together, we can make our polysaccharides. Some important monosaccharides that we'll talk about in just a little bit are pentose sugars, things like ribose and deoxyribose. And then those are our 5 carbon sugars. So penta means 5 carbon. And then our hexo sugar, which is glucose, which is in our blood. So those are kind of the main monosaccharides that we'll talk a lot about. So again, ribose and deoxyribose as our pentose, and then glucose as our hexo sugar. So again, these are just examples of some of the monosaccharides that we take into our diet: glucose, fructose, galactose, and then deoxyribose and ribose are going to make up, obviously, our nucleic acids in a little bit when we talk about them. And again, disaccharides are just where we're making a covalent bond, right, through that process of dehydration synthesis. So our disaccharides are too large to pass through cell membranes. This is kind of important to remember. These molecules are bulky, okay? And the reason why we don't carry all of our energy in the form of carbohydrates, the reason that we pack them in nice and condensed in the form of lipids, is because carbohydrates are just big and bulky. They're heavy and they're bulky. So if we had to carry all of our energy in the form of carbohydrates, we'd be like twice as big and like twice as bulky. Because again, that's just how carbohydrates are. So again, they're too large to pass through cell membranes once you're talking about things like disaccharides. Sucrose, maltose, lactose, you'll hear those. Those are some disaccharides that we'll talk about. And again, the big thing is that they're formed by dehydration synthesis. Okay, so again, you should know that for all of these organic compounds formed by dehydration synthesis. Okay, and so these are just showing you some examples of these monosaccharides that were put together via dehydration synthesis to form these disaccharides. Probably ones that you've heard of. Maltose is just glucose and glucose together. Sucrose is glucose and fructose together. And then lactose, if you're wondering, is galactose and glucose together. Okay. So kind of interesting. And then again, of course, polysaccharides are these polymers of many monosaccharides kind of put together through these dehydration synthesis reactions. Starches are carbohydrate storage that's used by plants. And so there'll be these really, really like complex polymers of these carbohydrate polymers. Really, that's what starches are. They're really complex polysaccharides. Okay, and then glycogen is the carbohydrate storage that's used by animals. So again, starch, carbohydrate storage for plants. Glycogen is going to be our carbohydrate storage in animals. And again, this is where we store like glycogen in things like our liver. It's also why we do things like glycogen loading. When you talk about, you know, trying to build up your glycogen stores before like a big run or something like that, okay? And they're not very soluble, okay? They're not very soluble in water. So again, these are what our polysaccharides look like with all of these covalent bonds that we made between the monosaccharides via dehydration synthesis, okay? All right, lipids, we're getting on to lipids here. So lipids contain carbon, hydrogen, oxygen, but less than in carbohydrates, and sometimes they'll contain things like phosphorus as well. Your lipids are going to be different because when we talk about these are not very soluble, these are completely insoluble. So again, you know, you can mix polysaccharides. Really complex ones aren't very soluble in water, but your simple simple ones, right? Your monosaccharides and your disaccharides, some of them are very soluble, things like glucose, right? We are here, lipids don't interact with water at all, okay? So, and you know this intuitively, right? Because if you mix water and oil, what happens, right? The oil separates and it will sit on top. It's actually much less dense. So, and that's kind of important to keep in mind, because if you take a glass of water, put a little bit of oil in it, you'll see that oil will sit on top. And that oil, being a lipid, is much less dense. And this is why we carry our energy in the form of lipids, okay? So we always talk about lipids and fats as being such a bad thing, but actually we really need them, because if, again, we had to carry all of our energy in the form of carbohydrates, we would be twice as big and twice as bulky. So fats are actually a really efficient way for us to carry kind of our more longer term energy storage, okay? So that way then they're lighter, they're less dense. It's a better way for us to carry our long-term energy stores, okay? So our main types are going to be triglycerides or neutral fats. Phospholipids, remember, they're in our actual cell membrane. Steroids are going to be a type of lipid. Important for you to remember that, especially as you get into 202, because it's important to remember that steroids are lipids and can move more easily through cell membranes. And then eicosanoids, which we'll talk about in just a minute here. So again, you can watch this animation. It's gonna talk. I'm not gonna
butter, lard, margarine, and sourdough are composed of lipids called.
I'm not gonna do this animation for you, because you can take the time to do it at home if you'd like. But all it's doing is talking about how you make a fat molecule, okay? So all you're gonna do is you're gonna have this glycerol backbone, as you probably remember from 181, and you're gonna have 3 fatty acid chains. And what reaction?
Fatty acids bind to a molecule.
What reaction are you gonna have to attach those fatty acid chains to that glycerol backbone? You got it. Dehydration synthesis, okay? So dehydration synthesis is the reaction that will be used, again, to build your triglyceride, okay? So triglycerides are neutral fats. Again, it's a glycerol backbone with 3 fatty acid chains that were added via dehydration synthesis. Okay? And so when we use the term fats, just so you know, fats are solid at room temperature. Oils are liquid at room temperature. So that's the difference between the term fat and oil. Our main function of, obviously, our lipids is energy storage. It also provides insulation, right, and helps us to hold in some of our heat to help maintain homeostasis, our internal body temperature. And then it also is going to provide protection, cushioning for some of our organs. So if you think in the abdomen, we do have, again, lipid stores around our organs, again, to help buffer some of those organs, right? To help protect some of those organs. Okay, so when we talk about triglycerides, again, yeah, I know you guys have heard this many times, so I'll go through this briefly, but they're saturated fatty acids that you can add on and unsaturated fatty acids. As you probably know, saturated fatty acids have no carbon-carbon double bonds. So that means that the carbons are completely saturated with hydrogens. And then unsaturated fatty acids are going to have these carbon-carbon double bonds. So that means that, you know, this carbon doesn't have a hydrogen where it would have up here, and this carbon doesn't have a hydrogen. So it's unsaturated, okay? And that carbon-carbon double bond provides a kink in the chain. And if you can picture, again, these kinks in the chain, what happens is when you form the triglyceride and they have these kinks in the chain, they don't pack together as nicely as they would here if you had a kink in the chain up here. And so what that does is that allows unsaturated fatty acids to stay liquid at room temperature. Now, the reason that when you talk about saturated fatty acids, they stay solid at room temperature, that's because all of these 3 fatty acid chains are saturated. And so they pack nice together. You can see, like if you had 3 of these chains, right? They pack nice and dense together, and that allows them to stay solid at room temperature. So saturated fatty acids are going to be things like animal fats and butter, which originally comes again from the milk of an animal, right? Now, unsaturated fatty acids, again, are going to have 1 or more carbon-to-carbon double bond, and it's going to cause this kink in the chain, and that's what allows us to have that liquid at room temperature. Now, our trans fatty acids, our trans fats are unhealthy fats, right? When we talk about trans fats, and now they, you know, include them on all of your ingredient lists. So when you look at a normal unsaturated fatty acid, a normal unsaturated fatty acid will have what's called a cis formation bond. And this just has to do with the way that things are, the way that this double bond, that carbon-carbon double bond here is formed, and how those hydrogens are around the formation of those hydrogens around those carbons. Okay, I'm not going to get into cis and trans just because, again, hopefully you already know that. I just don't have time to get into it, so I can go over it with you if you need more. But all I want you to know is that, again, an unsaturated fat is your kind of your normal unsaturated fat is your healthy fat because it has these double bonds in the normal cis formation. That's normal, okay? To form this trans bond, what we have to do is we actually have to force hydrogens back on into, and they end up coming on in this transformation. So it's an unnatural way of forming these fatty acid chains. And so what ends up happening is on these trans fats, the reasons that we originally kind of liked them is that the trans fats end up forming this chain that packs nicer together. And so basically we ended up increasing the longevity of some of our shelf foods because these fats would stay more solid at room temperature, okay? Because you can see they kind of form they don't have these big kinks like the unsaturated ones do, okay? And so we used to use them in a lot of foods to kind of extend the shelf life of them. They could also say, oh, well, we have lower saturated fat because the trans fat doesn't count, right, as saturated fat. But again, then we found out that these modified oils are really unhealthy for us, okay? And there's lots of reasons I don't have time to get into right now, but there are lots of reasons why these trans fats are unhealthy for you. So again, that's just something to note the difference between, you know, trans fats and your normal, naturally unsaturated fatty acids there. Omega-3 fatty acids are, again, the ones that are just supposed to be really heart healthy fatty acids. Again, things that are going to come from things like fish, you know, tuna here, flaxseed has so omega-3 fatty acids. And those are the types of fatty acids that will help you produce the good cholesterol versus the bad cholesterol. Okay. And then trans fats kind of increase your production of bad cholesterol. So those are why those are kind of, these are not healthy, and that's why those are healthy, kind of the short of it. Again, this is just showing you that dehydration synthesis reaction that we already talked about to form triglycerides. Phospholipids, these are just modified triglycerides. So here you're going to have your glycerol group, and then you're going to have a phosphate head, which is going to be charged, okay? That's why it's hydrophilic, remember? So that's why this end is going to be charged, and it's going to want to interact with water molecules. And then you have this tail region, which is your fatty acid chains coming off of that glycerol molecule. And these are going to be nonpolar, hydrophobic, and not want to interact with water. Again, they're lipids, right? So that's what's so great about phospholipids is phospholipids are this kind of like, you know, chimera, right? Of both, you know, your hydrophobic and hydrophilic ends. So that's why I love phospholipids. They're just cool. And so again, in your phospholipid, you have this polar region with that charged phosphate head, and then this non-polar region that makes up kind of the sandwich middle of your membrane, remember? And that's going to be the lipid portion of your bilayer, okay? So what that means is that in your cell membrane around here, so here those phosphate groups are charged and they'll interact with other charged things like water here on the extracellular and the intracellular side. But here, these lipids here in between won't allow things that are really charged through, okay? Because they're lipids. They don't like to interact with charged things. So that's what makes our phospholipid bilayer such an important structure, okay? That's why it's a good doorman of the cell, okay? So here's your typical phospholipid. Again, the charged phosphate head, glycerol backbone, and the 2 fatty acid chain. Steroids are important because they are these 4 interlocking ring structures, and our common steroids are going to be cholesterol, vitamin D, our steroid hormones, like our sex hormones, corticosteroids, things like cortisol, aldosterone, and then our bile salts. So again, you're going to get into those once you get into 202. Now, cholesterol is kind of an important thing in our cell membranes because cholesterol actually helps to keep our plasma cell membranes and the structure of our plasma membranes more stable. So it actually helps to increase the fluidity, believe it or not, of the membrane by kind of keeping these phospholipids from becoming too packed and tight together. So it really helps to keep our membrane fluid, and those cholesterol molecules are really important for that. So, and they're again an example of a lipid. The most important steroid again is cholesterol. It becomes the building block for things like vitamin D, for steroid synthesis, so the steroid hormones in our body, as well as bile salt synthesis. And again, it's a really important structure for maintaining the fluidity of our plasma membrane. So again, when you look at a steroid, it's just these 4 interlocking hydrocarbon rings, and that's the base for our steroid, okay? And then different structures coming off of those 4 interlocking hydrocarbons are going to differentiate what one steroid is from the other. So again, cholesterol is the biggie. It's the basis for all steroids formed in the body, cholesterol. Believe it or not, we think of it as bad, but it's actually really important, right? So cholesterol kind of gets a bad name. It just depends on what types of cholesterol transporters. So when we talk about like cholesterol is a bad thing, we're actually talking about the cholesterol transporters, not actually cholesterol itself. Because cholesterol is really important, right? But our LDL, when you talk about our LDL is actually just the cholesterol transporter. And unfortunately, it transports that cholesterol into our arteries, right, on the walls of our arteries, so it's bad. So we want the HDL, the good cholesterol transporter, that transports cholesterol to where it needs to go instead of on our artery walls, okay? Eicosanoids, we won't talk too much about these. They more are derived from kind of these fatty acids called arachidonic acid found in our cell membranes, and they're most important for our prostaglandins. So our prostaglandins are an important hormone that plays a role in blood clotting, blood pressure, inflammation, and labor contractions. This is all going to be kind of more your 202 stuff. But it's just important to keep in mind that prostaglandins have this lipid base to them, okay? Kind of interesting, there is a role of eicosanoids in kind of the widespread inflammatory response in SARS-CoV-2 infections. It's kind of interesting in terms of the role of the eicosanoids in the kind of inflammatory storm. So prostaglandins are released as part of that kind of inflammatory storm in SARS-CoV-2. So I'm not going to get into that because obviously that's way more than what I have time to get into, but I just like to bring it up in terms of, you know, the actual real life application for eicosanoids. So you're welcome to read. If you're interested, you can read more on this. You don't have to. Again, it's just way more advanced than what you need to know, but I just thought I would bring it up there. So lastly, we're going to talk about proteins, and then nucleic acids are our last two organic compounds. Proteins, you probably know, again, have a variety of functions. They're structural, they're chemical, they make up our enzymes, right? Really important. They're important for muscle contraction. And they're obviously polymers of our amino acids. Our amino acids are the monomers, and we put those amino acids together with peptide bonds to form our polypeptides or our proteins, okay? And then what makes those polypeptides into actual proteins is the structural folding of that. So again, hopefully you've already had this, so I'm gonna go through this really briefly, but all proteins are made up from just 20 types of amino acids, and we put those amino acids together in different ways to make different polypeptides. When we join one amino acid with another amino acid, it's joined by what we call a covalent bond, it's joined by a covalent bond called a peptide bond, okay? So again, I'm not going to go into this because you should already know that it has an amine group. It has a side chain that determines what type of amino acid it's going to be in a carboxyl group. And again, we have 20 different amino acids because we have 20 different R groups, okay? So again, just like any other organic molecule, when we put two amino acids together, we're going to do that dehydration synthesis reaction to form our peptide bond, okay? If we need to break a peptide bond, we're going to do hydrolysis to break them into their individual amino acids, okay, right? Pretty easy. Now, there are 4 levels of protein structure, okay, that are going to help determine its shape and function. So the primary structural level of a protein is just its simple linear sequence. Okay, so here's the primary structure. It's just amino acid 1 attached to amino acid 2, attached to amino acid 3 here. This is the primary structure, just simply the sequence of amino acids that are bonded together, okay? Now when we get to our secondary structure is going to be how those primary amino acids start to interact with each other. And what's going to drive that interaction? You got it, the R groups, okay? What type of R groups and how they're charged or not charged is going to depend on how they're going to interact with each other, okay? So that's why the sequence of amino acids and the order that those amino acids with the different R groups are in is going to determine how it's going to fold, okay? So Our secondary structure can either be that it will fold in some areas into an alpha helix, that's a coil, okay? So like this, and again, our R groups are going to determine that. Or is it going to fold in what we call our beta sheet that kind of zigzags, okay? So kind of zigzags back and forth like this. And you'll see that, you know, some proteins, well, if I can do this real quick, some proteins will have a section that has, you know, alpha helix here, and then all of a sudden it'll have beta sheet here, and then maybe over here it'll have alpha helix again. So again, you know, that secondary structure, it's not limited to only one of those per protein. It can have both alpha helix and beta sheet in different areas of the protein, okay? So that's a secondary structure. Now, tertiary structure is how though that secondary structure kind of folds back on itself. So these are how the secondary structures, the alpha helix and the beta sheets, interact with each other, okay? And so that looks like this. How do, again, these secondary structures kind of fold back on themselves and interact with each other? That's tertiary structure, okay? And then quaternary structure is simply when you have two or more polypeptide chains, each with its own tertiary structure, combining to form a functional protein. So here you have one polypeptide here with all of its tertiary folding, another polypeptide here with all its tertiary folding, and now they're interacting together to form a quaternary structure. Okay, that's all that is. So our shapes of our proteins can be either more fibrous or globular, just depending on what their structure is. And we're going to talk about different fibrous structural proteins that are going to have, again, more of this structure. So they'll have a lot more alpha helix in its secondary structure. And these are going to be more strand-like. They're typically water insoluble and pretty stable. And again, the reason that these are going to be important is because they form more of these like fibers type structures with their kind of tertiary and quaternary folding. They're going to be more important for mechanical support and tensile strength. So these are going to be things like keratin in your fingernails, elastin, and collagen. We're going to talk about elastin and collagen strands in your tissue. These are just, again, these fibrous proteins. And collagen is actually the single most abundant protein in your body. It really provides some good kind of structural tensile strength. And so certain contractile fibers will also fall into that. But those are some really important fibrous proteins. Then we also have lots of globular proteins, which is just like it sounds. They form these big globs, right? They're compact, they're kind of spherical. They're usually more water soluble, but also usually more sensitive to environmental changes. So they can kind of unfold more easily. And these guys have really important tertiary quaternary structures. So these are going to be things like antibodies, hormones, molecular chaperones, and especially enzymes. So our enzymes are a big globular protein. And because of that, they're typically going to have these really functional regions that we call active sites, okay, where they can bind substrates, okay. So those are your globular proteins. Now, globular proteins are more susceptible to denaturation, where they would unfold and kind of lose their 3D structure. So, fibrous proteins are going to be much more stable, where globular proteins are going to be more susceptible to denaturation, okay, basically denaturing. And when a protein denatures, its active sites become deactivated and it's no longer functional. So if you have an enzyme that denatures, that's bad because that enzyme can no longer function to help speed up that reaction, okay? So this can be caused by a decrease in pH, or it can be caused by an increase in temperature. And so this is, again, why homeostasis is so important. I can't emphasize that enough. We maintain a certain body temperature, or we maintain a certain pH even within an organ so that it can provide that ideal environment for the specific enzymes that are there, okay? So our different enzymes will have very specific pHs that they like to function at. And we have to maintain that because if we can't, then that protein can denature and it's no longer active, and it's no longer active as an enzyme, okay? So sometimes this is reversible if normal conditions, again, are restored, but if the temperature change or the pH change is way too extreme, we can't undo it. It's just like cooking an egg, right? Once you cook an egg and you've really denatured those proteins in an extreme way, you can't go backwards, okay? Keep in mind that, remember, enzymes are these globular proteins that act as catalysts, again, and they're going to increase the speed of our chemical reactions without actually getting used in the process. So again, they're going to lower the energy that's needed to initiate that chemical reaction. And this will lead to an increase in the speed of the reaction. Yay! Right? So that's what enzymes do. Enzymes here have an active site. They'll bind their substrate, okay, speed up that reaction that would have occurred anyway, but make it occur at a much faster rate, and then release the products and that enzyme be unchanged. It can go bind another substrate now. So that's the beauty of enzymes, okay? And all they're simply doing is they're lowering the energy, what we call the activation energy that's needed to initiate or make that chemical reaction occur, okay? So this leads to an increase in the speed of a reaction. I shouldn't say make that chemical, but initiate that chemical reaction. So again, all they're doing is speeding up the rate of that reaction. That reaction would normally happen, it would just happen at a much lower rate than if the enzymes are present. Okay, so this allows for the millions of reactions that happen in our body per minute. Again, if we didn't have enzymes or all of those metabolic reactions that we would need for our body to function would happen way too slow, okay? So many of our enzymes do require what's called a cofactor. So a cofactor or a coenzyme to activate that enzyme. So this is important because we're going to talk about this in 202 a lot, where there are these cofactors. Maybe it's a metal ion that's required for that enzyme, and that's why your body requires that metal ion. Or it's some type of organic molecule, oftentimes even a vitamin, that is required for that enzyme to function, okay? So that's what we call so out of this slide, really what I want you to get is that those cofactors and coenzymes are going to be, you know, metal ions in this case, or again, something like a vitamin that we have to take in that's required for our enzyme to function. And without that cofactor, without that coenzyme, that enzyme is not functional, okay? So that's kind of the big thing I want you to get with cofactors and coenzymes. Again, enzymes, as you know, already know, are very specific. They act on a very specific substrate. So enzyme 1 will only bind substrate 1. Enzyme 2 will only bind substrate 2, okay? And each enzyme will have its own specific cofactor or coenzyme that's required, okay? Or pH that's required. Also, you probably already know this, the names of enzymes usually end in ASE and are often named for the reaction that they catalyze. So hydrolases are going to, again, they're going to speed up hydrolysis reactions, okay? Oxidases are going to speed up oxidation reactions, okay? So it's nice when they're actually named after what they do. And again, enzymes are just lowering that activation energy, the energy that's needed to initiate a reaction. So I love that this you can see this nice little diagram of lowering that energy barrier, lowering that activation barrier. And so again, enzymes will allow chemical reactions to proceed quickly at our normal body temperatures. And the 3 steps that are involved in enzyme action, it's really easy. Substrate binds to the enzyme's active site, okay? And it forms the enzyme substrate complex. Then that complex undergoes kind of a conformational change and rearrangement of the substrate, resulting in a final product, and then the product's released from the enzyme, okay? So it's pretty basic. So again, this is just showing you without an enzyme and then with an enzyme how that activation energy is lowered, okay? And then this is just showing you again that enzyme. So here, the enzyme is going to bind the substrates at the active sites, and it forms the enzyme substrate complex. Then it undergoes a conformational change and rearrangement. Product is produced, and then the product is released, and the enzyme returns to it is basically unchanged and ready to bind more substrate. Okay? So that's pretty basic. I know this went a little bit long, so I'm really going to try to go through this super rapidly because you should know nucleic acids, okay? Again, nucleic acids are going to be made up of our nucleotide nitrogenous bases, okay, attached to a pentose sugar attached to a phosphate group. And our two classes are going to be DNA molecules and RNA molecules, okay? And here in DNA, remember we have our nucleotide bases, cytosine, guanine, adenine, and thymine. And then in RNA, we have the same nucleotide bases except for thymines replaced with uracil, okay? So pretty easy there. RNA also is single-stranded. DNA is double-stranded. And DNA, again, it holds our genetic blueprint for the synthesis of all of our proteins. We'll get to that in more of the cell chapter, okay, coming up here. So again, DNA is a double helix, and it's going to contain your adenine, guanine, cytosine, thymine, okay? And again, you have that complementary base pairing of adenine with thymine, guanine with cytosine. This is a little more kind of involved than we really probably need to know, but again, it just kind of gets you back to the basics, just to kind of remind you. Hopefully you've had this so many times, it's super familiar. So again, and this is how that double helix, again, is going to form. Remember that you have the hydrogen bonds here between those bases, those nucleotide bases of each of the strands that are intertwined to form the double helix of DNA, okay? RNA, again, is going to be important because it's going to link our DNA to protein synthesis. So we'll talk about RNA in the form of its process in transcription and translation. So again, RNA is single-stranded. It contains a ribose sugar instead of here it contains a deoxyribose sugar. So big difference there. A thymine is replaced with uracil in RNA. And again, there are three varieties of RNA that we'll talk about in the next chapter: messenger RNA, transfer RNA, and ribosomal RNA. Lastly, our last nucleic acid that we're going to talk about is ATP, adenosine triphosphate. So you have that adenosine nucleotide base attached to a ribose, and again, it's an adenine attached to a ribose sugar. So there's your nitrogenous base, ribose sugar, and then it's going to be attached to 3 phosphate groups in this case. And it's those 3 phosphate groups that are the high energy bonds that provide the usable energy that all our body cells need, okay? So that's the structure of ATP. It's important to understand, again, that is that adenine nitrogenous base attached to a ribose sugar. So that's the RNA nucleotide with, again, a phosphate group and then 2 additional phosphate groups. So that's why it's called adenosine triphosphate, 1, 2, 3. And it's these phosphate groups that are the high energy bonds, right? That's what stores the energy that all of our cells need. And this is the energy, again, those high energy bonds are why ATP is the energy currency of our cell. Okay, so this is the high energy phosphate bonds that we can actually hydrolyze to release energy. Okay. And so that's just showing that reaction as we break down those bonds. So as we break adenosine triphosphate into adenosine diphosphate, and we break one of those phosphate bonds and then release that phosphate group, we're going to release energy in the process of that. And that's the energy that can be used to do work in the cell. Okay. So, and then we'll talk about the different types of work that that energy can be used for as we get into the different chapters in the cell. So we'll talk about how it can be used for transport work, mechanical work, and chemical work, but I won't get into that too much right now. Okay, phew. That's it for chemistry. I'm going to stop us here. That was enough. If you have any questions as I went through that really quickly, please, please, please come see me.